to understand how this white dwarf Sirius B can not collapse despite this immense pressure, we're going to have to delve into the wonderful world of quantum mechanics. And once again, this started in the early 19th century, when people were first measuring good spectra. Fraunhofer himself was one of the pioneers in this, with the discovery that when you get a gas and heat it up, it gives a spectrum looking something like this.
So this is essentially one of the, it's a tube containing, in this case, copper and argon, and it's something we would put on a telescope. And when you put an electric charge to there, the thing glows like a giant neon sign. And when you take a spectrum of it, where we plot wavelength versus intensity, you can see that all of the light coming out of this tube of copper and argon isn't just, a black body. Rather, you have discrete colors. So you have, for example, very bright places where there's a lot of light coming out, and then essentially nothing. And there are literally, in this case, hundreds of these spectral lines, as we like to call it, emerging from copper and argon. And it turns out if we made a gas of hydrogen or something else, you get a different set of lines depending on what it's made out of.
This is really weird. Why, when you have a gas, does it emit light or absorb, depending on its conditions, at particular wavelengths, not everywhere? Now, by the early 20th century, the standard model of an atom was something like this. You got the protons and neutrons in the middle and the electrons orbiting around the outside, and people were thinking it was like a solar system, only smaller. This is grossly not to scale. To scale, this is 100,000 times smaller than the orbits out here, so you wouldn't even see it. But if something, a situation like this, it kind of seemed to make sense. We knew our own solar system had things sucked into orbits by the gravity. So you do the same thing here. You've got the positive charge in the middle, the negative charge on the outside, so things would orbit. But the trouble is, whenever you get a charge that's moving in a circle requires centripetal acceleration. Acceleration means it radiates, so it would radiate energy and spiral in very, very quickly to the middle.
Yeah, that's right, because you get, every time an electron accelerates, it's going to put out some light. And in this case, you're going to have a bunch of orbits that can be in random orientations. And so you expect to get sort of almost any color of light depending on the conditions of the orbit. And of course, it's not going to be stable. Eventually, you're going to end up with the electrons down in the center.
Also, the electrons can have any energy they like. There's no particular, it's not as if some orbits are allowed and some aren't.
That's right.
The solar system, I think, could orbit stably at any distance from the sun. So it could be any energy, so any wavelength.
And yet we know that this, whatever we think's going on, you're going to get discrete little places where you have, these energy coming out. So it's like they can only do certain things. So that's kind of a funny situation.
It's really puzzlesome. Why does the stuff only put out at particular wavelengths? What's forbidding it from having a wavelength halfway between two of the lines, or 25% between? Well, people's thinking about this, and there is an analogy on Earth. There is a situation on Earth where you can get a spectrum which only has particular wavelengths or other ones, and that's actually musical instruments, discovered all the way back in prehistoric times. So if we take a guitar and pluck the string, you hit a particular note, and I recorded that note, and here's what its waveform looks like. So what you're seeing is air pressure varying, and
so it's quite a regular pattern. It's not a beautiful sine wave, but the pattern repeats. You can see this little thing here, and so you have a real distinct pattern when you pluck a guitar string.
Yeah, when you pluck it, you hear a particular note. It was la, not some. It didn't sound like
That's
so
right.
if it was across all the spectrum, it was a particular note. What you can actually do is a spectral analysis of this. This can be broken up into multiple sine waves by a mathematical operation called a Fourier transform, and here's what you get. So this is the frequency and how much power there is at that frequency. And what you can see is just below 100 hertz, there's a lot of power. And then it just double that, just below 200 hertz, and just a whole series of integer ratios to this.
Yeah, so you have sort of 100, 200, 300, 400, 500, etc.
And a bunch of other ratios like 2 to 3, 4 to 5. These are the harmonics, which is what gives the guitar or any other instrument its particular characteristic sound. But this is just what we like. We've got a spectrum which is low in the most part, but with a whole bunch of narrow spikes. There's a huge lot of power here, but not halfway between it.
Yep.
So this seems to kind of work.
Okay, so let's think about why this occurs. Let's just look at what one of these strings is going on.
Okay, so here's a string. It's locked at both ends, and when you pluck it,
Boing. Yep.
it could vibrate like this. So it's got a fixed point, what's called a node at both ends, and an antinode in the middle where it vibrates as much as possible.
Right.
And that will give you the fundamental note, the first But then you can also get it doing something like this.
And so that would be going tuk, 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 twice as fast.
Yes, and that will give you the second spike, and you can also have third, fourth, fifth wiggles. And so these are giving you the spike, the spike, the spike. In all cases, you have to have an integer number of wiggles from one end to the other, so because it's fixed at both ends.
All right, so that is a way to get discrete things out of a musical instrument, but that sort of means that we need to have some sort of discrete set of orbits or something for the electron inside of an atom.
Yeah, I mean, for a musical instrument, you need two things. You need a wave, in this case
Yep.
sound waves, and you need to block it in.
Right.
So in the case of a guitar, it's a string with waves locked at both ends. In the case of a woodwind or something, it will be a sound waves up and down a column of air, once again with a barrier or some change at both ends.
Right.
So in principle, you can do this in 3 dimensions as well. So for example, if you had a wave trapped in a spherical cell, like if you could make an electron a wave, which is weird, but if you could make a particle as a wave and you could lock it inside an atom, it wouldn't be as simple as 1 dimension, but you get actually patterns like these.
So these are patterns in 3 dimensions, and you can see like this pattern is nice and kind of circular, but then you get these cloverleaf patterns and quite intricate looking flower patterns.
Yeah, so these have got waves bouncing back and forth in different ways in 3 dimensions.
Right.
And once again, you're getting standing waves, just like you do from sound. So if an electron was a wave, we need a wave, remember, to make it work. We need to lock it in place. The atom will lock it in place. So we get, if it was a wave and we could lock it in place, then you would get a series of discrete possible standing waves, which will give us the spectrum we like. But electron is a wave. It's a bit weird.
Well, I think we're going to have to understand the basics of quantum mechanics then, Paul, because electrons do appear to act like waves, don't they?
Mm-hmm.